associate to give you HCO3 minus plus H plus. Can you all recognize that the H2CO3 and the HCO3 minus are the acid and its conjugate base? Okay? Let's read. Just for you to understand. Now, when you get to the lungs, the alveolus is the small sac. Your lungs, if you look at the lungs, there are many small, like, okay, for the sake of the physics students, I'll say bags. Okay, basically, and in there, the carbon dioxide concentration should be lower than that in the blood. So it should diffuse out. Okay, and exchange takes place then. Alright? Okay. So, the first two diagrams were there for you to understand what you really need to understand in this part. Okay? When the H plus in the blood increases, there are many different reactions in the body that can produce H plus. For example, when you exercise vigorously, you will produce lactic acid. Okay? The HCO3 minus removes additional H plus, and therefore the pH remains unchanged. Now, I think this part is not so much in your syllabus, but I think you would like to understand this. Why is it so important that this occurs? Most of your body, okay, I'm going to be rude, but I shall not be, is made up of protein, a lot of it. Okay, the enzymes have a particular shape, very specific. If that shape changes, I see two people from the Olympiad class talking very excitedly. Don't turn around. Yes, pay attention. Okay. Now, where was I? I finished about bags. Okay, about the shape. Now, if you change the H plus concentration, the shape of the protein may get altered, and then it cannot function. Okay? And when we talk about proteins not functioning, basically can die. Okay. Now, so for the blood, basically, since most of the waste is acidic, it functions very well in removing H plus. Removing OH minus is not so done so easily. Okay? Okay? Okay, so now we have basically finished all the different types of calculations that you need to know how to do. Okay? Strong acid or strong base. There's weak acid or weak base only. There's a salt of the weak acid or weak base. There's buffers which are combine both the weak acid and the salt, or the weak base and the salt. Okay? So the last three situations, there are equilibria. So you need to know which equations to use are appropriate and how to calculate. Okay, so first of all, you need to identify, you must be able to identify, look at something and say, okay, this is a weak acid, or this is a salt of a weak acid. Okay, this is a weak base plus its salt. Because the calculation depends on the solution that's involved. Okay? The ones with the star, you need either the Ka or the Kb to solve. Alright? Done? Okay. Now, should you just use the original concentrations? No. It's a bit more complicated than that. Now, there are two things that you need to consider. When you have this situation, one, does the volume change? Okay? Are you adding two solutions or liquids together? So, second thing is there a reaction? If there is, then you need to calculate the new amount. Okay? The amount can either increase or decrease. Okay, which equilibrium constant should you use? Not so easy for you to figure out sometimes. Basically, if you think that it's going to be acidic and produce H+, you need to find the Ka. If you think that it's going to be alkaline and produce OH-, you need to find the Kb. Please take, I use the word produce quite specifically, because you need to understand, it doesn't mean, okay, if it's a weak acid, very straightforward, use Ka. If it's a weak base, use Kb. What happens when you have a salt? Okay, so if you have a salt, you need to think, if it's the salt of a weak acid, is it going to be alkaline or is it going to be acidic? I think I told you how to do this, right? An easy way to remember is, if it's a salt of a weak acid, it's alkaline. If it's a salt of a weak base, it's acidic. Okay? Can? Alright? Okay, so this part, basically you have learned how to do all the calculations. The next part is about indicators, and finally we will do the titration curves, which is actually application. Okay? Okay, acid-base indicators, how do they work? I mean, you have used this for years and years, but you may not have been taught how they actually work. Okay? Now, basically, you do titrations, you want to determine accurately the volume of acid or base to react completely. Okay? The reaction is complete at the equivalence point. Now, either you can detect this using an acid-base indicator, or you use a pH meter. Now, often people will say, we should use the more modern method, therefore you use a pH meter and so on. Now, why we still use indicators is because they are convenient and simple to use. To use a pH meter, you need one to be working first. And it's not as simple as that sounds, because last week Friday I spent like 2-3 hours trying to find a working pH meter and getting it to work. Then when you do the titration, eventually you will need to plot a graph. If you have everything hooked up to a computer, fine. But if not, each point you need to, each time you add the acid, for example to a base, you need to measure the pH, and then you need to take it down, then you go plot it. Okay? So it's a lot slower than doing using an indicator. Okay? and not to mention more expensive using a pH meter. This thing, which is a fairly good one, with some other probes, it costs about $900. And as far as scientific equipment goes, that's quite cheap. I remember asking my professor what some instrument in her lab cost, because I thought it looked like a piece of crap from like 1940s or something like that. And she looked at me and said 50,000. Okay? And she's considered that quite cheap. Okay. Now, the indicator should show you different colors in solutions of different pH. Okay? So, okay, take note, with base and the conjugate, okay, will have different colors. So, phenolphthalein. I guess you all have not used phenolphthalein. It's now considered to be carcinogenic. That means can cause cancer. Okay? So you haven't been exposed to it. This news comes 40 years too late for me. And I think there's a lesson in chemistry. Everything is a double-edged sword. What they tell you is good now, 40 years down the road may not be good. Okay? So, when you are told to take safety precautions in the lab, please do it. Because you never know what can come once they find out more stuff. Okay, so phenolphthalein. I'm not sure whether you can see the difference in the structure. What happens is it's colorless, and then when it's alkaline medium, one of the bond breaks, okay, and then there's an acid-base reaction, so then you get two OH minus. Sorry, 2O minus then. Okay, and that's pink. Okay, the color of the indicator depends on the relative proportions of the indicator in the acid form and the indicator in the salt form. Okay, so in this case, when in the acidic form, position will shift to the left. You get acidic form indicator, HIN, and then will be A, color A. Alkaline medium, position will shift right, and then you get color B. Okay? So, the pH equals to the P of the pK of the indicator, that's the log of the salt over acid form. Now, when you change the pH, the ratio of the two indicators will change. Therefore, the color will change. In the case of phenolphthalein, okay, usually the color changes when it is 10 times for example, the HIN is 10 times that of the IN minus, or the IN minus is 10 times that of the HIN. Okay? Now, translated to pH terms, basically it means plus or minus 1 of the pH, okay, of the pKa. That is what we call the working range. Okay? So, in selecting an indicator, you need to know over where do you want it to change color. Okay? Do you want it to change color in the acidic region or in the alkaline region? There is no one indicator that can function over the whole range. You all know, okay, you know, I know somebody is probably thinking universal indicator. Universal indicator is actually a mixture of many indicators. And then they will change color. Okay? And you can't use universal indicator in the titration because it will keep changing color. Then you don't know what color to stop at. Okay, that's the issue. If you want to use a universal indicator, then you might as well use a pH meter. Then you can actually track when the change is large. Okay, so we are looking now at all the different indicators that you have used. Without orange, I think you may not have used green without orange. Bromo, thymol, blue, probably not. Phenolphthalein, also not. What you use now is thymol blue, which is actually the same as phenolphthalein as in, but the color, similar to phenolphthalein, but the color is actually colorless to pale blue. Okay? That information, if it's not here, is in your titration notes. You need to remember at least two, methyl orange and thymolphthalein or phenolphthalein. Okay, I suggest you remember thymolphthalein because that's what the new syllabus uses. Okay, so the working range of the indicator must lie within the sharp change in pH at the equivalence point. Okay, what does that mean? Basically, if you plot a graph, it will end up like that. It must change color in where there is a jump in the pH. From a low pH, it suddenly jumps to a high pH. Okay? So, if you do that, then the equivalence point matches the working range. Okay, and then it's a good indicator to use. Otherwise, if you use, let's say for example here, methyl red, what will happen is that the indicator changes color before you reach the equivalence point, and then it gives you a false reading. It tells you that you have reached equivalence point, but actually it hasn't. Okay? So methyl red, you would think that the equivalence point maybe is 10, but actually it's not. The correct answer is around 15. Okay? Phenolphthalein, you can get the correct value. Okay, so the indicator should give a sharp color change at endpoint. Right? Now, the reason why you cannot use large volumes of indicators, right? Why must put one drop? Isn't more better? So you tell me put 1 and put 10. It's that these things are themselves acids and bases. And if you put in a lot, it will affect the result. The other reason I found out for myself is that you put a lot of indicator, it actually makes the color change less distinct. Because then you can't really see. Okay? Okay, so that is the end for this part. No, the worst is yet.